Alright, hey everybody, and welcome to the final video, I think, for this chapter, where we are going to be exploring a little bit more about the way the brain is structured in terms of what it is that we are perceiving, and also how top-down and bottom-up processing plays more a part in how we perceive the world. Alright, so again, if you've taken sensation perception, I know I keep saying this is going to be a little bit of a review for you. But those of you that are not as familiar with how the brain works, there's actually a distinction in where the brain processes different kinds of information. And so far we've talked a lot about how we've been processing visual stuff back here in the back of the head. So you can imagine that we have our eyes, right here. So it looks like an angry eye. I didn't mean him to be so angry. So this eye is, it's hanging out, it's looking around, and we have these connections that are coming back over here. And so back here is where we're going to be doing a lot of the basic feature detection that we've been mentioning. So a lot of the line angle, perception and stuff like that is going to happen back there. And from there, which is right here, we are going to then go on to, and they call this the V1, it is the first stop in the primary visual area. From there it's going to go to the V2, to the V3, to the V4, and then it's going to split off into all these different directions. This is, believe it or not, a simplified version of what goes on in the brain. It's actually way more complicated than this, but just for the sake of kind of understanding where this information goes. Essentially, we're going to have some information that is going to go up this way to the parietal lobe, and we have some that is going to go down this way to the temporal lobe. So in other words, once we have that visual information reaches this part of the brain, some of that information is going to come up this way into the parietal lobe, and some of it's going to go down this way into the temporal lobe. So we have this distinction. This distinction is going to tell us about what something is and where something is. So whenever something is moving up in this manner, that information is going to be what it is that we're seeing. Oh, I'm sorry. I was getting ahead of myself. This is actually where something is being perceived. So up here is where. And you even may remember that when we were talking about the basic lobes of the brain, we said that the parietal lobe was used for spatial processing, right? And part of that is because that's just where we see things, and that's where it's perceived and handled in the brain, is in this particular pathway. Sometimes you'll hear it called the dorsolateral pathway as well. Down here is where we have what is it that we are seeing. So that is going to go from here down this way into the temporal lobe, onto a specific structure called the inferotemporal cortex. So you can think about it like this. If you were to look at this, for example, what's going on in your brain is you are recognizing what it is, and that's handled by one part of your brain. And you're also recognizing where it is in relation to you and in relation to me. And that is being handled in a different part of the brain. And this is really kind of weird because we don't think about it this way. We don't think about it as you have, that you're splitting up this information like this, or at least I don't. I see this as like, oh, this is like one thing and this is where it is. But the way that our brains treat it is what you're seeing is a tape, what is this, Scotch tape dispenser roll, I don't know. That's what you're seeing, and it also happens to be in this specific location, or that there is something in this specific location and that there is something else called a Scotch tape wrap or duct tape wrap, and your brain is going to combine those things and say, all right, what you're seeing, this is where it is and this is what it is. But that those happen in different parts of the brain. So this is really kind of complicated because it creates a really strange problem, a problem that we're not going to solve in this chapter. We're going to solve it in the next chapter, about how our brains are able to combine that, because we don't see the world fractured like that. We don't think of where things are and we don't think of what things are as independent. Whenever you see something and you recognize what it is, you're automatically recognizing where it is as well. But that's not how our brains do that. So we'll talk more about how that happens in a later video for chapter 4. But before we get down that road, a little bit more explanation about the what versus where pathways and systems that we have. The what system, which is going to be the inferotemporal cortex, is going to be responsible for detecting what something is, recognizing what something is, identifying it. And the way that we know this is through lesion studies. We have seen what happens whenever people damage this part of their brain. What happens is that they are left with a very peculiar condition called visual agnosia. So, sometimes I will tell you, oh, go check out this video or whatever. This is one of those videos that people at the end of the semester still remember. So I highly recommend checking out this video because it will stick with you. It's a very good representation of what visual agnosia is. What would it be like to not be able to recognize what something is? We'll talk more about that, again, in the next chapter when we talk about object recognition. And also through lesion studies, we've found out what happens whenever someone damages this part of their parietal lobe, which is responsible for recognizing where something is. That leads to something called motion blindness. So it's not necessarily the case that they can't tell where things are, they just can't see motion. So it's really hard to tell where things are that are moving and in relation to one another. There's not a lot of really good representations of what this would look like on YouTube, but this is one very brief kind of example to help you kind of, for me, it was hard for me to wrap my head around what would that look like, and I think this video does a decent job. All right, so this is what's called parallel processing, that we have two independent processes that are taking place in the brain. However, we do not see the world as disjointed. We see it as a coherent fluid whole. And so that is called the binding problem. It is a huge problem. It's a problem in as much as it is like something that needs to be solved. And it's something that people still debate over. A lot of people, I would say the majority of cognitive psychologists, feel like the binding problem was solved in the 80s. But still, like I said, some people still argue about these things and about how the brain handles and processes this information. But we'll look more at that in the next chapter. Well, actually, I guess I thought that I was going to save it for the next chapter, talking about object recognition, but we're going to talk a little bit about it here too, I guess. And then we'll further talk more about it in chapter 4. So the binding problem is going to be quote-unquote solved through two separate kinds of mechanisms: neural synchrony and spatial position. And those are both they sound abstract, but really what this means is neural synchrony just means that that whenever we have things that are firing at the exact same time, we have a tendency to relate these things together and assume that they are related and try to put them together. We see that with vision. We also see that with sound as well. And we also have spatial position. So spatial position here is just saying that that whenever you have something that is active in part of your retina, that you are going to start combining those different things together and assuming that they are related. And we know this because we see what happens whenever people aren't paying attention, or whenever they have problems recognizing what or where something is by mixing these things up. That's called a conjunction error. And it usually happens when we aren't paying attention to critical features. So basically the binding problem is solved through where things are, the fact that our neurons are firing at the same time for both areas, that our what pathways and where pathways are firing at the same time, so we associate those things together. But we also need attention to take those features and really put them together, because we find that whenever we don't have that, that's whenever people have issues with being able to see where and what things are, and we'll typically kind of mix them up. So people that have parietal lobe damaged are going to be particularly likely to have problems with this, and that's the area that also governs your attention. So not only is this spot up here for spatial processing, it's also used a lot in attention as well. So here is a quick example. So if you are reading along with me, attention is critical for binding visual features. When attention is overloaded, people make conjunction errors. So I just flickered something on the screen very briefly there, and because you are probably looking at this text, you may not have completely seen it, right? So even though that information hit your retina and was processed by your eye and processed by your occipital lobe, chances are you may not know what it was, and if you do remember what it was, you may have swapped around some colors. And so this is what you saw, and whenever I show this in the classroom, usually what I get is that people will say, oh, it looked like a bowl of fruit. Awesome. But when I ask people to tell me where the colors were, that's where we start seeing some interesting diversions or divergences. That some people will often say they saw a lemon right here, and they saw grapes right here in the middle, or something to that effect. And the reason why that happens is because we get the information of what is being present. And we kind of get the information of where these things are present, but we don't do a good job of combining them. And so we mix up where these things are because we're not paying attention to them. If I were to take this away and then ask you to focus on this side of the screen, and then I were to show it like that, you would have no problem, right? Your attention is there. All right, sorry, I had a little bit of technical difficulty there. Let's move on to the next piece. We talked a little bit about this fruit jar and about how if you're paying attention to it, you have no issues whatsoever of identifying what those things are. So attention is critical in binding the what and the where information of what we see in front of us. So a little bit more about form perception, or how we start beginning to put together features. Obviously more on that is going to be in the next chapter, which is on object recognition. But I don't know if you heard my dog bark. But to get there, we're going to talk about Gestalt psychology. So Gestalt psychology, if you haven't heard of Gestalt psychology before, it was kind of a precursor to a lot of American psychology. So while behaviorism was going on in America, in Europe, Gestalt psychology was really, really big. And it was this belief that a lot of what we experience in the world is bigger and broader and greater than the sum of its parts. So what does that mean? Basically, it means that if you were to look at something, the most common example that I usually go to is like if I were to talk about your personality, right? We have different personality scales that can like tell you, how extroverted someone is or how open someone is and things like that. You can get 5 numbers that tells you about the person's personality. But if I got those 5 numbers and I tried to recreate a human being with those 5 numbers, they would be different than you, right? And the reason why they're different than you is because who you are is greater than these individual elements whenever you add them together. That who you are is bigger. And perception is exactly the same way. That what we experience is bigger than just simply what we sense. Just because like our eyes will detect all of these things and it'll process all these things, but our brain is still going to bring things to the table to help flesh out and make that experience bigger. So we're going to be talking about that in terms of sometimes you'll hear it called form perception, sometimes you'll hear it called principles of organization. But basically it is something that is going to help us solve the binding problem because it is going to automatically take care of some of this basic visual perception. So here are a bunch of really quick and simple versions of this. So in this case, what is that you see in if I were to ask you to describe these 16 circles, what would you say? You'd probably say, well, these are 4 groups of circles, 2 groups of the same color, and they're going down vertically, right? You'd probably say something like that. Or you would at least say that this row belongs together, this row belongs together, and this row belongs together. Not that this row belongs together and this row horizontally like that, right? And the reason why we do that is because we automatically tend to group things that are based on similar appearances. If I were to ask you to explain what you see right here, in the second piece, you'd probably say 3 groups of dots, right? Because we have some dots that are closer to one another, so that is proximity. That is the principle of proximity. We tend to group things together whenever they are close to one another. Here's another one. This one is called good continuation. It's called good continuation because when we perceive this particular object, we perceive a cylinder and behind it a green rectangle that passes through. We don't see a rectangle and two separate rectangles on either side. We assume that it is carrying on behind that cylinder. That is good continuation. This one is called closure. Sometimes you'll hear it called illusory contours. Essentially what this is, if I were to ask you what is this that you see, you'd probably say an interrupted triangle or a triangle with white in front of it, because it looks as if that these lines probably would carry on and complete a full line or full contour. And so that is an example of closure. And then simplicity, which is just that whenever we are looking at these things, we try to or we automatically perceive them in the simplest way possible. So, for example, if you were to see this particular design, you would most likely see this as one rectangle and a second rectangle, which is what you see right here. You don't perceive it as like a 12-sided dodecahedron or whatever the proper name is for that. You don't see it as two shapes that are just kind of split right here instead of two that are overlapping right there. So we try to go with the simplest way possible. Here's another example of closure or illusory contours. I included these because I like them. I think they do a better job of illustrating this. So like, for example, if you were to look over here on the right, this looks like there's an arrow or a house that is in front of these other items, right? It looks like there is some house like that, and that it is essentially in front of these black circles. That's cutting them off, essentially. That is not actually what our eyes see, but it's what our mind puts together. So in that way, this is an example of top-down processing. And in fact, all of these are examples of top-down processing. If we were just using bottom-up processing for something like good continuation, then what we would be seeing is just, two squares and this the cylinder. We are assuming, we are theorizing that this green is going to continue behind it. This is another example of good continuation. So this is an illusion, obviously. This young woman has a mirror, but you can see where it looks as if it is continuing right through her, right? Because the lines line up perfectly. This is another example of what's called figure ground perception. So whenever you see this, depending on your perspective, you might perceive different things. If you perceive the black as being a background, then you'll see the word lift. If you perceive the white as being a background, then you'll just see these different kind of black Minecraft looking blocks. Alright, this combines a lot of those that we've been talking about. It combines proximity, it combines illusory contours, it combines good continuation. So this word is the word perception, but we're able to, but there's not actually a single letter here, right? It's just we perceive there to be a contour right here, and a contour right there, and a contour right there, and a contour right there, because we know what to expect with language. But in fact, those lines don't actually exist. It's all in our head. So that's another example of top-down processing. Alright, so here you can see a picture of a cow. And so for this cow, oh crap, I didn't mean to tell you that immediately. I got ahead of myself. This is a picture of a cow. Usually what I ask whenever I'm in the classroom is I say, what is this? And people will guess and they can't quite figure out what it is. And it's not until I'm able to trace out certain parts they begin to recognize it. So if you can follow my cursor right here, I don't want to draw on it too much. But you can see that there's the top of the head right here. And you got the side of the head right here. And you got the fence behind it. You got an eye right here, and an eye right here. And so what is your eye actually seeing? Your eye isn't really seeing a cow, right? Your eye is just picking up on black and white splotches. It's your mind that once you notice, once you know what to look for, then you will see something that looks much more like a cow, right? You will perceive, little hair right there. You got an ear right there, an ear right there. It's the bottom of his face. It's got his nose right there. All right, so you should be able to see the cow now, right? All right, so that is a cow, but we're not actually perceiving that with our eye. Here's one final example. What is this? And again, when I ask this in the classroom, I get some people guessing, but really, what is it that our eye is seeing? Our eye is just seeing a bunch of white and black spots, right? It's not really seeing any animal. It's not really seeing any person or anything like that. So, now with the full picture, can you tell what this is supposed to be? This is actually a Dalmatian. So, if you don't believe me, let's trace it. You can see the ear right here, the nose down here. We got one leg right there, one leg right there, one leg right there, his tail over here, and then basically right there. So we got a Dalmatian. So we have a dog, and it's sniffing what appears to be maybe part of a sidewalk right there. We got, it looks like a shadow from a tree right there. Maybe a walkway of some sort right there. We have a dog that's just kind of sniffing around, right? Now, if we were to get rid of all of that, now what do you see? You see a dog, right? You see the same dog. You can't go back and erase what it is that you saw. And that's because whenever we first saw this image right here, we were experiencing bottom-up processing. We were using data-driven processes and perception. We were looking for what is it that our eyes are picking up on, and we couldn't really make sense of it right away. And so once we have an idea about what it is that we're supposed to see, when we go back to this, we can't unsee it. We can't go back and say, oh, now I can't tell what it is. I can't tell what I'm supposed to be looking at. No, we know what it's supposed to be. Here's another example of figure ground illusions where you can either see what appears to be these pillars, if you're looking at the white as the foreground. If you're looking at the white as the background, then you will see pairs of men or women looking at one another with their heads bowed a little bit. All right, I'm going to skip over this because we just talked about it. Here is one final piece that we're going to talk about. If you were to look at this dog and this dog, we know they're the same size, right? So we know they're the same size, and we can get a pretty good idea about why they're the same size because we have a reference point. We see that they are as big as this chair, right? And so we know they're the same size. So what are we using? We're using top-down processing because we're putting these clues together to figure out what it is that we're seeing. If we were just using bottom-up processing, we would say that, oh, okay, this dog right here, bingo, he is much bigger than his little brother right over here. They're different dogs. This one's much smaller than this one. But we know that's not the case. We know that the point of reference is different, and so we're using that to make a decision. That's not even something that we think about, though. That's something that we just automatically use. And that automatic sense of it is what's called an unconscious inference, where we're kind of solving these problems without even really thinking about them. I keep using the phrase automatic, but some people will object to my using that phrase. Some cognitive psychologists don't really like the word automatic because it implies that it's reflexive, which is more of a behaviorist type of way of looking at things. And it's not reflexive, but it is a process that seems to happen immediately and involuntarily. Here's another unconscious inference. If I were to ask you which of these tables has more surface area, you might say, well, I'm not sure which one you would say. I get different answers in the classroom for this. They're actually the same surface area. And if you don't believe me, you can pop out PowerPoint and you can flip these tables over and you'll find that it's exactly the same shape for these two. It's just that we're using an unconscious inference to do the wrong thing. Now we're using the unconscious inference to essentially misguide us because we're seeing the legs down here, and so we assume that this table must be pretty long if it's got these legs like this compared to this table right here. That this table might be wider, but this table over here is longer. In fact, they are the exact same shape, and you can turn the PowerPoint if you want to. Actually, I can do that right now. Hold on one second, folks. So if we wanted to, we could. I'm going to turn this around like that. I know you're holding your breath. You want to see if it actually works. Look at that, folks. Look at that. It's the same. How amazing is that? All right, so you get the idea. But again, this is top-down processing. Tells us, and this is an example of top-down processing leading us in the wrong direction. That top-down processing is telling us that these are two separate sizes. What bottom-up processing would tell us is that they are in fact the same size, because what the eye is seeing, how it is hitting the retina, what those cells are processing before they go into object recognition or even in parts of the visual cortex, is that these are the same size. They occupy the same amount of our retina. It's not until we get into the primary visual cortex that we start trying to figure out what it is that we're seeing. And that knowledge leads us into the wrong direction for this. All right, that's all we got time for. I'm going to catch you in the next chapter where we'll talk about chapter 4, which is object recognition. We're going to pick up immediately right off of this stuff. Thanks for tuning in. I'll see you later.